Thank you.
Okay, I guess I just want to first start with problem number 6 in section 11.1. It talks about the first search algorithm so that there is unlabeled vertex. I mean, is it just that the graph is disconnected, or am I just totally missing something?
No, you are not missing anything, and I want to make sure. Were you comfortable with with 1 and 4, right?
With one, I think so. I mean, I have them done.
Yes. If you have them done, you should see that in problems like 1 and 4, all the graphs are connected. Am I correct?
Right. Yeah.
If the graphs are connected, what are the things they were saying in 6 is not going to happen, because if the graphs are connected, you are going to label all the vertices.
Right.
So this 6, whatever this will happen only if the graph is disconnected. Will have different components.
Okay.
So once you finish labeling things in one component, then you are done. Then you are forced to start labeling brand new in another component. Am I making any sense?
Yeah. I just thought that that was just like not enough as an answer. I don't know.
So what that will gives you is these collection of edges. You will get a spanning tree. For example, if you look at problem number 4, you got a spanning tree, right?
Yeah.
So in problem number 6, you will get a spanning tree in each component. So spanning tree in each component. So you are going to get overall a spanning subgraph. That means you are going to have all the vertices, but that is not going to be connected. So you are going to get a spanning subgraph, and it will help you to find how many components are there, how many connected components are there in the overall graph. So it's like 1 or 2 lines.
Okay.
You can only tells you that this procedure will give you a spanning tree in each component. So overall, you are going to get a spanning subgraph, but which is not going to be a tree.
Okay.
So you're sort of counting how many components are there. So the subgraph determined by the marked edges is going to be, frankly, a spanning subgraph. That means all the vertices are going to be there, but that's not connected because it's in different pieces.
Okay.
Yeah, just write 1 or 2 sentences. Is that make sense what I'm talking about? You know, that seems not enough. The only reason is 6 is there. The main question they want to answer is problem number 7. 6 is sort of a precursor for problem number 7. But I gave only 6, but I haven't asked 7.
Okay. So, but we only have to do 1, 4, and 6 in that section, right?
Yes. Yes.
Okay. Okay. Okay, that makes sense. I just wanted to make sure that I wasn't missing anything, I guess.
Sure.
And then in section 11.2, just so that I am clear with the bridges, I am looking at some of these going, there are no bridges in them.
Yeah.
And it's only a bridge if it's connecting 2 different components with 1 edge. Is that correct?
Sort of, in a sense, you are absolutely right. But here you have to be more careful. For example, in 11.2, 1A, you don't have any bridge, right?
Right.
But if you look into 1C, do you see any bridges in 1C?
Yeah.
Can you tell me one bridge?
Like D to E.
D to E is one bridge.
And then A to B.
A to B, exactly.
And then G to F, or G to H.
Awesome. Those are all different bridges. So you are absolutely right. So AB, it's not looking like a connecting different components, but if you remove AB, A is going to be isolated, right?
Right.
Yeah, so you're right.
Okay. And it can only be like one set. So like if you look at B, you can't disconnect D to B and D to F at the same time. It's just
no, it's just one edge. It is just one edge.
If it's just one edge taken out, then
exactly. Okay. Because if you take collection of them, that is possible in anything. You can almost erase all the edges and make everything disconnected. So it doesn't make any sense.
Exactly. Okay.
And there are things which you say collection of edges, but that is called edge disconnectedness, but we are not going there.
Okay.
Yeah, but for this bridge means just one edge. That's it.
Okay. What, I guess for number, I always tend to miss problems on the ones where I have to prove something, like number 10. It says prove or disprove, and then like number 11, it says prove. I did number 10, but I wanted to talk about number 11 for sure, just to know that, it looks like you have to do it both ways, correct? Because it says if and only if. So not only do I have to prove that an edge is connected, graph G is a bridge if every chain is whatever, and then do the backwards, the converse.
Yes.
Okay.
And before I go there, what did you prove for 10? You proved or disproved? When you said disprove means you need to give an example. Prove
Right.
means you need to give some kind of an argument. What do you think is the answer?
Well,
Correct?
I thought that it was to prove it because of theorem 11.1.
Mm-hmm.
Because I said if a graph has a cut vertex, then a bridge exists in the graph. And so therefore a connected graph with no cut vertices has no bridges. So then by theorem 11.1, if G is connected, it has no bridges, so it is strongly connected because of the given.
You did an awesome job. You did a great job. So I think Valerie joined in. We are talking about problem number 10 on 11.2, Valerie. Hopefully she can hear us. So you were right. That is the thing. And but only thing is you said that if a cut vertex exists, then a bridge will exist, right?
Yeah.
So that statement is not correct.
Okay.
Because there are graphs which I can draw. You can find a cut vertex, but it might not have any bridge.
Okay.
So you can say this, but whenever a bridge exists, cut vertex always exists.
Okay.
Because if you take any bridge, if you remove one of the vertices attached to the bridge, then you are automatically removing that edge as well. So that becomes a cut vertex. Am I correct in saying that? Do you understand what I'm talking about?
Can you say that one more time, please?
If you take any bridge,
Right.
and one of the ends of the bridge has to be a cut vertex, because bridge means what? If you remove that edge, the graph is disconnected. That means if you remove one of the ends at least, then you're removing the edge as well, right?
Right.
So one of the ends has to, sometimes both might be cut edges, cut vertex, but one of them has to be a cut vertex.
Okay.
So here they were saying it has no cut vertex. That means it has no bridge.
Okay.
Because there is a bridge, you should have a cut vertex. But in problem number 10, they were saying that is a connected graph with no cut vertex. So you should say this. Since the graph has no cut vertex, it will not have any bridge as well, because one of the ends of the bridge has to be a cut vertex. If you want to write me down, I'll write it down.
Okay.
Maybe I'll write it down. Where is share content? No application window. Are you guys seeing the PowerPoint, folks? Blank PowerPoint?
I am not.
No, I don't see anything.
Okay, let me share application. I will click PowerPoint now. Hopefully you'll see it now. Are you seeing it now?
No.
Nope.
Oh. Okay, let me stop sharing. Let me share it. Try it again. 1 minute. Are you guys seeing now?
Nope.
Nope.
Hey, that is surprising. I'm seeing it here. You're not seeing PowerPoint at all, sharing a window.
Nope. Just a shaded little guy picture thing.
Man, that is not good. Because I am sharing it and it is telling me I'm sharing something. Application window. Are you seeing it now, folks?
Nope.
Nope.
Hey, that is not good. Okay, let me use the whiteboard then. Okay. Are you seeing the blank whiteboard now?
Yes.
Yes.
Okay. So for 10 pro, okay. I am talking about problem number 10 in 11.2. I'm just telling you how to write it. Because this whiteboard is not very interactive. So you will say the graph has no cut vertex, right? No cut vertex. So since G is a graph, with no cut vertex, again it'll react a little bit slow, so you might be see after a while. So G has no bridges. Why it is not putting a dot there? Since if G has a bridge, then at least one vertex of the bridge has to be a cut vertex. One vertex of a bridge is a cut vertex. So what we can say is G is a connected graph with no cut vertex. G is a connected graph with no bridge. I am so sorry, this is not responding very good with no bridges. So by 11.1, so by theorem 11.1, G is strongly connected. You almost got it, Chelsea, but the only thing is you said the graph has a bridge or something. You said the first statement is not right, so you need to change it like this.
Okay.
Do you understand it well?
Yes.
Okay.
I'm looking to see.
Okay, I'll give a minute for you to look at it. We are talking about problem number 2 in 11. Sorry, problem number 10 in 11.2. Prove or disprove problem she is asking.
Did you get mine that I sent you? I worded it a little wordier, but
Oh, you texted me or something?
I did. I sent a copy of it because the two proofs were the ones that I'm not sure about.
Oh,
Send
let
it on
me
your
look.
phone.
Oh, you sent me on my phone. Okay, my phone is pretty screwed up. Let me bring my phone. I'll check. In the meanwhile, you look at it. I'll bring my phone. Just a sec. Hey, Val, you just sent me 10 minutes back or 15 minutes back. I'm just looking at it as we speak. Cut word happens when G has a bread, so G cannot have a cut word when G cannot. Yes. Well, I think your problem number 10 proof looks good to me,
Okay.
because that is exactly you wrote.
Yeah, I got a lot wordier.
Yeah, that's fine. You can be as wordy as you want, as long as you're right, you're good. But normally, what is happening is you try to give so many examples. Normally, when you prove by an example, there is a possibility that things will screw up. So I have to read your 11, but in the meanwhile, I'll ask Chelsea, you have a question about 11 or you are good?
Yeah, that was my question, was number 11.
Okay. What exactly you have a question on? You have to prove both sides. You have to assume if the graph.
I don't really have anything, because I just want to understand where I need to go for the proof, because I feel like I try and start something and then I think I'm going somewhere and then I turn it in and it's wrong. So I just want to make sure I'm on the right track. I mean, I guess that connected graph.
It is comparatively, there is not much proof you can write per se. Let me, can I erase this so that I'll start problem number 11?
Yes.
Sure.
In problem number 11, it is sort of, it is a little bit vague in a sense. You want to prove if the graph is a bread, connected graph, if is a bread. See, you take this. I am proving in one side. Suppose G is a connected graph. And I will call this edge U comma V is a bridge. What exactly that means is, if you remove this U and V, this graph will become two pieces. Am I making any sense? That's what the meaning of that, right?
Yes.
That means G minus E is disconnected. That means if you take G minus E, the graph is going to look like this. There are two portions. So U is going to be on one side and V is going to be on the other side. Am I right?
Yes.
So then it is sort of clear to you, if you want to go from U to V, this is the only way you should be able to go, because if there is some other way, which from U to V you can go without using this edge, that means if you go like this, then this edge cannot be the bridge, because even after removing this, the graph is still connected. Am I making any sense?
Yes.
So so G minus E is disconnected with U comma V or in different components. Well, my handwriting, this is C, not E, by the way. So, Andrew, I'm talking about problem number 11 on 11.2. So here, if G is a connected graph and E that is a bridge, then you need to show every chain from U to V should have that edge UV. So you will simply say that is a bridge, so that is disconnected, and with U and V are in different components. Then you can say in your own words, if there is a chain from U to V which doesn't have UV, then UV cannot be the bridge, because even after removing this, Oh man, I don't want to clear it. Okay, man, there is no way I can erase this. Because if there is another chain like this, even after removing UV, this is still connected. So that's what you can write in your own words. So if there is a chain, man, my handwriting is not so great in this case because this whiteboard is not very responding very well today. So if there is a chain from U to V, which does not include the edge UV, then G minus C is still connected. So which is not right, which is wrong, right? And you can say this clearly works in the backward direction too, right way, because it is pretty much if and only if each and every statement. For example, if the other way also you can write in your own words. If every chain from U to V uses edge UV, that means if I remove that edge UV, then U and V are going to be disconnected from each other. That means I cannot reach from U to V or V to U. That means G minus E is disconnected. So that has to be a bridge.
Okay.
That is what you need to write in the backward direction. So in the backward direction, you can simply say if every chain from U to V includes U and V, so once you remove UV, U and V cannot be reachable from each other. So that means G minus that edge E has to be a disconnector. So that means E has to be a bridge.
Okay, that makes sense.
Yeah. Andrew, is that making sense, man? I know you
Yeah,
joined a little bit.
I don't know how to get these proofs started. Like my brain just thinks through things, but I don't.
I completely understand. That is the reason this is comparatively an applied course, but I tend to throw one or two proofs, but just don't be disheartened by it in a sense. Like as long as you get the concepts correct and you got the problems are getting correct and if you get the idea, most of the times I see that you have the idea when you're explaining things, but sometimes what happens is you're trying to exhaust all cases. And in proof, it is impossible for you to exhaust all cases when you're writing an assignment. So please bother me in a sense, like whenever you do write something, just send me and say, is that make sense? Then I'll immediately reply and correct. It is a learning process. I am more interested in your learning than like getting 100 out of 100 in each assignment. That is not the purpose. So
Right. Did you
yeah,
did you look at my 11 to see if I was even is that just way off base?
let me check 11 because you sent me 10 minutes back. I need to change my phone. My phone is so bad I cannot even tell you. Yeah, I'm talking about iPhone 4 or something I'm using. But is if in a graph G there is a chain that starts U and go to G. You are getting the idea, but I certainly when you're saying G0, G1 and all that stuff, you're saying P equals to R plus 1. Uh, that is, I cannot pinpoint out where it is wrong, but it doesn't feel right.
Okay.
You know what I'm talking about? Am I making any sense? If you would be removed, because you were saying, for example, in that case, if you would be removed, it would be a cut vertex. Then G could be disconnected. I know what you mean to say, but the way you're wording it there, if you use removed, that is a cut vertex. That is not a right statement. If that is a cut vertex, if you know that is a cut vertex, removal of that will make it disconnected. But just by removing something doesn't make it a cut vertex. But what you mean is, if you know that is a cut vertex, if you remove it, that makes it disconnected. That's what you want to say, but you're not wording like that there.
Yeah.
Yeah. So I certainly prefer if you write it the way hopefully you can read my handwriting, however atrocious that is.
Okay.
Yeah, just a sec. Yes, Andrew.
So
You have a
sorry,
question, Mike?
yeah, sorry I'm late. I just got on. I had a question about number 11, trying to read through the problem.
Okay. Okay, you are talking about problem number 11 in 11.2, right? That is what I'm talking about here.
Yeah, I just got in and I'm kind of reading through the proof because that was one of my questions, was number 11.
Oh yeah. Please take your time. I will help you to understand. What the problem number 11 says is this: if the graph is a connected, and if there is an edge from U to V, if you know that is a bridge, then you need to prove if and only that every chain from U to V. That means if you go from U and V, that has to go through that edge UV.
Right.
So it is an if and only if condition. That means you need to prove this. You know that graph is disconnected, that is given to you. And if you know that edge UV is a bridge, then you need to prove every chain from U to V should include that edge. That is one side. And the other side is if every chain from U to V includes that edge, then that edge has to be a bridge. That is on the backward direction.
Okay.
Am I speaking too quickly here?
So I guess my question is, how do you go about proving that every point has to go through that without using the definition of what a bridge is?
Yes, that is what I did here. Are you looking at the whiteboard here?
Yeah.
Yes, on the whiteboard, I simply said is this. Suppose the graph is connected and this edge is U to V. Hopefully you can see the pointer. Are you seeing the pointer?
Yeah.
Yeah, this is a bridge. What exactly is the meaning of the bridge? If I remove it, then the graph should become at least two parts.
Right.
And U has to be in one part and V has to be in other part.
Right.
Right? They both cannot.
Yeah, otherwise, it's not a bridge.
Otherwise, it is not a bridge. You are absolutely correct. Because that is they have given that is already a bridge. So once you remove that, they both should be in two different parts. So if there is a chain from U to V which doesn't include this edge UV, that
Then
means if there is a path like this, then that is still connected even if you're removing this. So that is not going to be a bridge anymore.
Right.
So
I guess that's what I'm thinking through, but I don't know how to write that as a proof.
Oh,
like, it just seems obvious. Like if it is a bridge, that's the definition of bridge. That's the only way to get back and forth.
I know sometimes in math you feel like that you know what is going on in your mind, but putting that in words is not easy. So don't worry about it. And that is the reason I try not to emphasize too much on proofs, because I know you might have taken the proof course long back.
Yeah.
But it is a learning process. So don't worry. After a couple of courses, you will get much better than what you thought you will be. So, but that's what you need to write. So,
I do have a question of, is a cut vertice always on the edge of a bridge? Does that make sense? Like, are the edges of a bridge always a cut vertice?
can you say it again, because your voice is sort of cutting out?
So the two vertices of a bridge, are they always cut vertices?
Yeah, the ends of the bridge are always cut vertices. You are absolutely right.
But every cut vertice doesn't necessarily make a bridge.
Not really. That side is not true. Every cut vertex might not be a bridge, but every bridge, at least one end of the bridge has to be a cut vertex.
I think there was one diagram where you had cut vertices but no bridges. But everything else was like the cut vertices were on the edge of the bridges. Right?
Yes, there are some graphs which have some cut vertices but no bridges at all.
Right.
But if the graph has a bridge, that has to have a cut vertex. If you look at problem number 10, for example,
yeah, that's I think what I said. 10.
Yeah, the says a connected graph has no cut vertices. I already wrote the answer and I erased it. If you go into the recording, you can see the proof there.
Okay.
You will see the recording in 1 hour or so, but I'm going to explain it to you here again. In problem number 10, they were saying a graph is connected graph and has no cut vertices. So you can clearly say, since the graph has no cut vertex, the graph should not have any bridge. Because if the graph has a bridge, one of the end has to be a cut vertex.
Right.
Am I making sense? So you can clearly say that is a connected graph which has no cut vertex, so it shouldn't have any bridge. So
But you
that is a
can't-
connected graph with no bridge. So from theorem 11.1, it should be strongly connected.
You can't say the other way around and say,
You cannot say the other way around. That is the reason that is not if and only if.
right.
So if you are not getting the proofs, please don't get frustrated, because I can understand the frustrations, because that is the fun part of the math. In a sense, it makes you mad sometimes, but that's okay. I wrote the proof for a 10, Andrew, and if you go back into the recordings after 1 hour, 1 or 2 hours or so, then you can clearly see the proof.
Okay, I'll do that.
But I just wrote the same things what I said to you in words, in 2 sentences, not more than 2 or 3.
Yeah, I think I had a good understanding of 10.
Yes.
That I was kind of confused about, and then number 6 from 11.1.
Yeah. Now is 11 make sense? Even you can write the other way the same way. If every chain from U to V if includes UV, then by removing U comma V, then they should be in different components. So that's exact same thing you're writing in the backwards, really.
Right.
Yeah. Well, is that making sense, Valerie?
Yeah, the parts of it are.
Okay.
I'm trying.
And no problem. You are doing great. Just don't worry about it. And any other questions, guys? You can see that this assignment is very much linked. The problems, for example, yes, Andrew.
Yeah, I had a question about 11.16.
Oh, 11.1. Man, we all have the same questions then, which 11.16 it says is this. Can I erase this portion? I'm going to clear this.
Okay.
Yeah.
Yeah. In 11 point, if you observe, I'm assuming you all had done 1 and 4. Am I right?
Yeah, I got 1 and 4. I think.
Yeah, you had 1 and 4. If you observe, all the graphs are connected. So you, using the procedure, you all labeled everything. Am I right?
Yeah, I think I got everything correctly.
You labeled everything. So the only time the depth first algorithm ends and you have to start again a new vertex, new labeling is if the graph is disconnected like this. It has 2 pieces. For example, if your graph is like this is the overall graph. Then you will put 1, you will check this, you will put 2, you will check this, and 3. Now you have to start a new labeling here. You should put 1 and check it, 2 and check it, and 3 and then check it, and then 4, right?
Is it the idea like you can't type idea? Like you can backtrack and keep your pencil on the paper, but if you ever have to lift the pencil to move somewhere else, then it changes basically.
Sort of the same idea, but it's pretty much really the same idea. But that means it says that happens when the only graph is connected. So it gives you that procedure will gives you the connected spanning tree in each component. So it gives you the overall, if you combine all the edges, you are going to get a spanning subgraph. That means you'll have all the vertices, but that graph is not connected, so it is not a tree.
Right.
So you can say in your own words, the subgraph is going to be a collection of spanning trees in each component, really. Or you can say you'll get a spanning subgraph, but which is not a tree. That means how many number of times you lift your pencil from the paper, you will have that many components. If the graph has 3 pieces, then you have to lift your pencil from the paper 3 times.
Right.
Yeah. And you might have observed that there is more than one answer. There are different kind of spanning trees you will get depending on the neighbors you select. Any more questions, guys?
Nope, I'm not sure what to ask anymore.
Okay, then great. And is that Chelsea or Valerie?
That was Valerie.
Okay, then if you have no questions, you can log out. Andrew, you have any questions because you walked in late, little bit.
No, I'm gonna go back and look at the video, probably at 10, and then write up 6 and 11. So that was it.
Sure. And you can submit even on like until Sunday. And if you have any questions, please ask me again. I am more than happy to meet you guys again. So please, and then I will sign off.
Thank
Okay.
you.
Sure, anytime. Take care, guys.
Yep, thanks.
No problem, man.